So
Your entangled
yes,
presentation.
this free will requires new physics. So we have freedom is an axiom. It can neither be proved nor rejected by any scientific experiment. So, I think freedom, like Nicholas said in the previous discussion, is something you can accept or reject. But if you are doing science, you can take freedom as an axiom for your science. You can do science also without freedom. But if you wish to do science with freedom, you can take freedom as an axiom. But I wonder why a deterministic universe produces a guy like me who wishes to be free. That is for me a paradox. Anyway, if I choose the option of freedom, I have to reject the determinants of the classical physics that we have discussed about before. And the true quantum randomness is in principle good news, very good news for free will. But there is an objection: quantum indeterminism excludes any order or plan, and therefore is incompatible with free will. This is a standard objection. The answer to this objection is that this is a misconception about the principles of the quantum. Quantum physics establishes that the detection outcomes in an experiment have to fulfill a determined statistical distribution. And this outcome is unpredictable in principle for an external observer. However, quantum physics does not establish that the outcomes must happen without any order and be meaningless. Thus, free will required new physics is the same as asking, can quantum randomness be controlled by free will? I would try to answer this question introducing first of all the accent of non-locality at detection, that is science, and in a second part I will make some scientific speculation about non-material control of neural networks. So here you have a simple quantum interferometer. You have here light emitted by the source, and this light will be captured. Oh, what is happening here?
So, Antoine,
yes.
can I suggest you do it on that screen?
Yes, okay. That is. So, and here is this light can go to this detector by this path or by this path. You can change here the length of one path, and what quantum physics predicts is this distribution here, and according to the length of these two paths. For instance, in this case, you have the distribution, you will get 70% of counts here and 30% of count here. You can also make so, and then you are changing this distribution here. So this will work so. For instance, now it's going so. Okay. Again, quantum physics tell you which be, with this particular configuration, the distribution of the countings here. But quantum physics cannot, they renounce to predict the order you are getting here, okay? And this already, in this experiment, means that you have two possibilities to say the decision of which detector fires is done at the detection, or it is done here. If it is done at the detection, decision at the detection, this means that there is a kind of coordination between these two detectors. If one detector clicks, the other doesn't click. and vice versa. So there is a coordination between these detectors. And this means that here you have already a sort of non-locality. You can put these two detectors quite far away from each other, and then this means that if there is a coordination, there is something which is non-local. Otherwise, if it would be local, you would be sometimes the two detectors firing, and sometimes the two detectors, neither of the detectors fired. This would mean you would have a conservation of energy on the average, but not in each single quantum event. So I think this is a quite important aspect of non-locality, because it shows that non-locality, if you assume that it happens, the decision at detection, non-locality is not only related to the issue of no signaling, as we have heard by Antonio, but also quite important related to the issue of the conservation of energy. So here, the principle of conservation of energy is being supported by non-locality. Something quite material, like the conservation of energy, requires something non-material, non-locality. You could take, if you take the decision here happens at the beam splitter, then you have to introduce the weird, then you have to assume that a particle is going one path and the other path is going an empty wave. It is the model of de Broglie, a wave that you cannot detect at all. So that is, I see, weird, a bit an odd concept in my opinion, because you are assuming the same thing propagating in space-time is undetectable, is unobservable. So that is a kind of contradiction here. So that is why I keep to the concept of non-locality at detection. So this is for me important, because if you can have this non-locality here at detection, then you could influence this order here, what is happening here, you could influence this like an influence from non-material, from outside the space-time. So this is now referring to some kind of non-material influence. And you could here introduce a certain order in this, like you could influence the order who is coming here from outside space-time. Nonetheless, when you finish this influence and you let the system going on, you will get, after new runs, after a certain number of runs, you will get this probability predicted by quantum physics. I would say, for instance, if I am now influencing the movements of my lips, when you are going to sleep, then you are having random processes in your brain, and then you balance in a certain sense, you reach in a certain sense this distribution you wish to have. So then, this simple experiment is for me the entry in the quantum world. So when you have the interferences and the photoelectric effect, that is here, thank you, and the photoelectric effect, then you are entering quantum physics. Photoelectric effects means that only one detector click at a time. That you send one photon, you have one of the two detectors clicking. So I say that is, for me, I compare this to the platform 9 3/4 in Harry Potter. So you are entering the magic world of quantum physics.